Hello, ELT132. This is Roger Young, and today's discussion, specifically this one, is going to be on counters. Now, we're going to have several videos regarding counters, but I want to go over the basics of a counter in this video. So what you can see here that I have already listed is I have basically three things. I have a count sequence table. That's what this is right here. All right, it's a table. Then we also have a state diagram. That is down here. All right. And finally here we have a timing diagram, and we'll talk about that in the end. But basically, if we start in the beginning, a count sequence table, if you look at this, we count from 0. This is your least significant bit. Remember, this is your most significant bit. So this is 0. The next one, so I'm going to write it here on this side. How's that, right? I can go 0, 0. I have it here. Do that again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So how many rows are in that table? Well, we're starting at 0 and we end at 11. So there are 12 rows in that table, right? So if we come down to the timing diagram, you're going to notice that we start at 0, then we go to 1, 2, 3, 4, 5, and we go all the way around, right, to 10, 11, and then back to the beginning, 12. Do you see how a state diagram and a count sequence table are similar? The difference, obviously there are differences. Here you have an arrow between every single state, right? And it tells you basically where you're going to go. Where is the next state? You can just follow the arrow. Here obviously you don't have arrows. It's in the table format, but you get the idea. And there's a picture of a clock in your textbook, and I thought that's just a great example of this, right? I mean, you start at 0, and they have 12 here obviously for a clock, but it's 0, 1, 2, 3, 4, 5, 6, all the way around 10, 11, and you're back to start again, right? Now, regarding this table, there's something called full sequence and truncated sequence. This is a truncated sequence table. And the reason why is we could still count further with 4 bits. So what comes after this one? This is 11. What would come after this one, right? It would be 12, 13, 14, and 15, right? So 15 would be 1, 1, 1, 1. All right, this would be 15. If you counted, if this counter counted all the way to 15 and then recycled, it would be a full sequence counter because it made use of all of the bits there, right? This is the maximum value that a 4-bit counter can give you, and then it would restart. That would be a full sequence, but here we have a truncated sequence, all right? Obviously, the state diagram is of a truncated counter, sequence counter, right? Because we could still have more states in here for a full sequence counter, but we don't have it in this case. And finally, let's look at the timing diagram, right? If you look at the timing diagram, notice I'm just drawing lines, trying to draw lines down here. You see how it You see what? Jeez, this is terrible. You think you get an idea what I'm trying to do here. I'm trying to Okay, that one's pretty good, right? Let's draw this one down. Let's draw this one down. You get the idea. Now let's look at this group right here. Right, we're coming down here like that. So in this case, this is your least significant bit, right? It's Q0, least significant bit, and then this is going to be your most significant bit, right? So we're 0, 0, 0, 0. We're right at this one right here, aren't we? Now what's this one? 1, 0, 0, 0. We're right here. This is going to be 0, 1, 0, 0, which means we're at 2. 0, 1, you know what? This is going to be 0, that's going to be 1. Did we show the 0 here? Oh yes, we did. Okay. I didn't know if that came through all right. But as you can see, you can go through each one of these states where transitions take place. It's on, it looks like it always happens right here on the upper edge of the clock signal, right? The rising edge, that's where you have this transition occur. So anyway, you could keep going down here all the way down. You know what? I'm getting better at this as we do it here. Jeez, that one's not too good. I'm trying to do this faster. Now, let's look at the last one. What's the last one going to be here? It's going to be 1, 0, 1, I'm sorry, 1, 1, 0, 1, right? So what do we have? 1, 1, 0. I guess it's supposed to be a 0 right here. I'm sorry, 0, and then 1. So this actually right here is 11, isn't it? And then here's your final transition right here, right? We draw an arrow right there. There's your final transition. And then what do we have? 0, 0, 0, 0. And it starts back here again. It starts over again. Or if you look at the state diagram, we went from 11 to 0. We start over again. So basically you have 3 different methods of looking at your counter. And I wanted to make sure you understood them. Here is your state diagram. It contains arrows and it shows you which state you're going to go to next. You have a count sequence table. The table lists each sequence in order. And then if the last sequence, it's the last one, if it recycles, it's going to have an arrow going back to where it's going to recycle to. And then also you have a timing diagram, and you should be used to these by now. And these you can follow to find out each state, and it's synchronous, so it has to be related to a clock pulse, right? There are 2 types of counters. You have full sequence. I'm not going to write sequence, my writing's not good. So I'm going to say full sequence, and you have truncated. So remember the difference here. When you use a full sequence counter, if you have, for example, 4 bits, right? You're going to go all the way up to 1, 1, count from 0 all the way up to 1, 1, 1, 1, and then back, right? Unless you have a counter that's going in reverse. But you make use of all of these bits to you can get the maximum value of all your bits. If you use a truncated, you're going to use less than the maximum value. And in this example, we only went up through 11 and back to 0. So that's a truncated counter. I hope this explanation has helped you. And in the next video, we're going to talk more about the circuits that are used to make counters. Thank you.